All right. Hi, everybody. This is Tori Hetterman from Norwegian Polar Institute talking, and Donald Slater in the background from the University of Edinburgh, I think. This is the second session of this workshop on ice-ocean interactions from the Joint Commission with the same name under IACS and IAPSO. We had a nice session earlier today already with presentations from Aidan Jenkins and Madeline Roosevelt on turbulence in the ice-ocean boundary layer. And now on the second section, we want to zoom out a bit and talk a bit more about the regional setting, the glacial melt and ocean dynamics, both around Greenland and around Antarctica, how this is seen in models, represented in the models. Just a few practical notes. As before, the sessions are being recorded and shall be posted online on YouTube afterwards. You may consider that when you raise your voice. This does not apply to the breakout rooms. They will be on your own, but in the common sessions, that there will be a record. And we will also try to synthesize what is being discussed in the breakout groups that happen after this session into a kind of synthesis report that we can refer back to as kind of hopefully a productive outcome from this workshop. So, said that, the program for this session is split in two halves. First half is the scientific presentations from Rebecca Jackson and Nico Jourdain. Small introduction of them coming soon, and then in the second hour we have these breakout groups where we really encourage you to join for discussions. In the first session, it was such we had kind of 90 participants on the presentations, and then about a third stayed in for the discussions. And it's not such that these breakout rooms become super crowded, because we can produce as many as we want. So please feel free to stay for the second hour and also share your opinions or share your ideas, or just meet with other scientists and ask all your questions that you're carrying with you. So, as you see here, topics of these sessions are on tidewater glaciers, testing how parameterizations work against real observations, and that is mainly containing Greenland, and then in the Antarctic, how we today implement ice shelves in ocean models and how those may affect the wider ocean circulation. That is split for two experts to talk to us. Dr. Rebecca Jackson from Rutgers University. She is taking lead on the tidewater glacier Greenland part, where she has worked both in the field and with theoretical approaches. And for the Antarctic, we have Nico Jourdain from Grenoble. He is, well, I got to know him as an ice shelf ocean interaction modeler, but I think he has done quite a bit other things on climate as well. So yeah, I guess two bright minds having more interesting things to say about the subjects than I could give you with this introduction. So I leave them speak for themselves. Once again, yes, yeah, I think this is just the next slide for the breakouts. So I think from here I just give the word to the people who shall serve content instead of me serving framework.
All right, great. Thanks, Tori. I guess I'll share my screen. Hopefully you can see these slides okay.
Yeah, and Becca, just to say, I'll put my hand up when you've done 18 minutes, and then I'll tell you when you've done 20.
Okay, perfect. Thanks, Donald. And yeah, thanks to all the organizers for inviting me and organizing this workshop. I'm excited to be here this morning or evening or whatever time it is where you are to talk about submarine melt at tidewater glaciers with a focus on the observational side and how we can link those observations with our existing theories and parameterizations. So I'm going to be focusing on tidewater glaciers and fjord systems common in Greenland, Alaska, West Antarctica, Patagonia. So a little bit different focus than from the first session this morning. We have relatively vertical grounded termini at these tidewater glaciers with inputs of submarine melt and subglacial discharge, as well as icebergs calving. And typically these tidewater glaciers flow into fjords, like the one shown here in a satellite image from a fjord in West Greenland. And so, thinking about submarine melt and the controls on melt, of course, involves a whole variety of scales, from large-scale ocean dynamics and atmospheric dynamics down to boundary layer processes and plumes right near the ocean-ice interface. And what I'm going to focus on for these 20 minutes is really some of these smaller scale processes of how can we understand submarine melting as a function of the ocean properties nearby and the subglacial discharge at the base of the glacier, really with a focus on what observations do we have and what observations do we need to have a better validated theory and parameterizations for submarine melting. I'm totally skimming over the motivation for why we might care about submarine melting of glaciers. Hopefully that's something that's familiar to this audience. And I'm also really not going to do justice to the really large number of modeling, theory, and laboratory studies on this subject, since I'm trying to bring an observational perspective here, but linking it with what we know from models and theories. Okay, so first, why is submarine melt so hard to measure at tidewater glaciers compared to other icy places that we might be familiar with? First, these termini are not floating, or not entirely floating, so we can't sort of leverage a lot of the approaches that we use for icebergs, ice shelves, and sea ice, where if you can measure the volume above the ocean surface or the elevation, you can track changes in the below surface volume of ice. But those sorts of approaches that have really developed a lot in recent years, especially new exciting methods for icebergs, can't really be applied for these near-grounded termini. We also don't have a stable platform to drill through. Common approaches for ice shelves and sea ice is we drill through and we can instrument the boundary layer, but that's not exactly possible for these calving termini. On the glacier side, there's pretty good constraints on total frontal ablation, so measurements of ice velocity, thickness, and terminus change can give us the sum of melting plus calving. But arguably calving is just as hard to quantify as submarine melt in these systems, so we're left with a lot of difficulty partitioning between the two. And then last, maybe not so different than some other environments, icy environments, but tidewater glaciers are incredibly hazardous and inaccessible right near the terminus where we want these measurements of submarine melting. So overall, we have a real lack of observations of direct submarine melting. But I'll mention kind of two approaches that have been getting us some of these numbers observationally. So one, maybe the most widespread approach for measuring submarine melt at tidewater glaciers has been looking at ocean fluxes or budgets, where the basic idea is that if we make measurements of ocean velocity, temperature, and salinity at some location in a fjord or the ocean, we can try to calculate the budgets of heat, salt, and mass for the water upstream, and then use that to infer the total submarine melt flux coming off the glacier. So this has been used in a growing number of studies, but there's some big challenges. One of the problems is that it can include a significant amount of iceberg melt in this estimate. And so if you're trying to get the terminus melt, you might be lumping that together with iceberg melt if you have significant iceberg quantities upstream of your ocean measurements. The ocean measurements are incredibly difficult and expensive to get because this method requires really good resolution of the velocity field across a fjord, as well as water properties. And then temporal variability in these fjords can be a real complicating factor for getting to well-constrained melt rates. And I should also mention that these give you only the bulk submarine melt flux, not the local melt rates or the spatial patterns. And so the upshot is we have some estimates from this approach, but they do have very large uncertainties, and there's also sort of a variety of methods that have been used with some inconsistencies. Okay, so the second approach I want to mention is a new method developed by Dave Sutherland in this 2019 paper, and being further applied by Nicole Abib in some of her ongoing work. And these are arguably sort of the first direct measurements of submarine melt at a tidewater glacier. And the idea is that using multi-beam sonar, the change in the terminus position can be tracked. And then using radar for ice velocities, the ice velocity can be removed from that submarine change in the terminus. And then if locations of iceberg caving are discarded, end up with melt rates and notably, information about the spatial patterns of the melt rates across the terminus. So this is, an exciting development. But overall, in thinking about the state of our kind of direct measurements of, or even sort of indirect measurements of melt at tidewater glaciers, we're left with currently very few observations of submarine melt and at a very limited number of different systems. And we definitely don't yet have measurements of how melt is changing in time. So if we're thinking these questions of how is ocean variability or atmospheric variability driving changes in glaciers via submarine melting, we certainly aren't yet at the point where we're measuring that change on really any timescales. Okay, so given this lack of observations, the field has relied really heavily on theory and models to represent melting. And so I want to kind of outline or remind people of sort of the most common framework for thinking about melt, particularly as it's applied at tidewater glaciers. So this is very similar to probably some of what was talked about in the earlier session, although with a focus now on how it's being applied for tidewater glaciers. So the first part of this kind of common framework is buoyant plume theory, which is a well-developed theory to track the mass, momentum, heat, and salt budgets for a plume as it rises along an ice face. And it goes along with an entrainment parameterization. And this tells us, given some inputs of buoyancy, how the plume will evolve as it rises along the ice face. And then typically for tidewater glaciers, this is coupled to a melt parameterization. And this then relates the plume velocities, temperature, and salinity to the melt rate. And in this formulation, it's assumed that melt scales linearly with the vertical velocity. So this is assuming a shear-driven boundary layer where the transports of heat and salt across this inner boundary layer are scaling with the plume velocity. I'm putting these equations here, and you're going to see this slide a lot as I kind of talk through different aspects of it. But hopefully, if you're not familiar with equations, you can think more in terms of the schematics down here. But what's nice about this framework is that it creates a nice self-contained theory where if you have measurements of your fjord temperature, salinity, and you have an estimate of the subglacial discharge flux, you can use buoyant plume theory to model these near ice properties. And then that in turn goes into the melt parameterization to get you melt rates. And the melt rates in turn feed back as a source of buoyancy to buoyant plume theory. And I'll refer to this as kind of plume melt theory when it's coupled together. So it's nice, it's self-contained, it's very tractable. And so we've seen a real explosion of using this in all sorts of different ways to model melt in tidewater glaciers. And this is a very, very incomplete list of all the ways that this has been implemented in the past decade. It's been used kind of just on its own. You would take this set of equations, you can look at the dependence of melt on stratification or discharge or whatnot. It's used to force the boundary of ocean models with the velocity field at the ice face, and it's used to force the boundary of glacier models with melt rates. Sometimes just the melt parameterization is used on its own in models that are high enough resolution that they can actually resolve the near ice velocity. But I'm going to kind of lump these together because those models are also modeling very idealized plumes that are effectively well represented by buoyant plume theory for the most part. And I'm, of course, skimming over a lot of details here. And then a fourth way is that this theory is often used to create a bulk parameterization, that you can boil this down to some scalings for how the total melt or the maximum melt varies as a function of ocean thermal forcing or subglacial discharge. And these coefficients do vary a bit depending on how you do this, but usually it's something like ocean thermal forcing with a linear scaling and subglacial discharge to about the 1/3 power. And this is a nice paper just out by Donald looking at estimating melt with this sort of approach for a whole inventory of glaciers around Greenland. Okay, so with all these studies, we have, if this plume melt theory is correct, we've now learned a ton about how melt varies with all sorts of things like ocean temperature, grounding line depth, spatial patterns, seasonality, interannual variability. yada, 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 a long list of things. But a lot of these results do hinge on the validity of this plume melt theory. And so I want to spend the next 10 minutes just going through where we have evidence to support this and where we have some challenges for understanding melt. Okay, so the first thing I want to mention is this growing body of evidence that melt seems to be very underestimated at tidewater glaciers when we apply plume melt theory. And this is emerging from a few different approaches. On the left, I have melt rates from Dave Sutherland with the multi-beam sonar approach, showing melt rates across the terminus on the order of 6 to 10 meters per day, whereas standard application of plume melt theory would suggest more of a terminus average on the order of less than 1 meter per day. Similarly, these are some results from evaluating ocean budgets, showing submarine melt as a function of subglacial discharge. And the observations fall up here, whereas the predictions from standard plume melt theory are these colored curves down here. And then these are not the only papers that have pointed this out, and there's, I'd say, a growing body of evidence that melt, particularly melt away from discharge plumes, is being underpredicted by theory. And so to kind of dig into this, and look back at this this theory, I want to point out 4 aspects that really need testing with observations. And I think some of these components are already well underway, and we have kind of good preliminary results about how we can test certain these 4 aspects. And as you'll see, others, I think we're just at the beginning. So one sort of problematic piece we have on the left-hand side here is that we have some unconstrained parameters for modeling plumes. For example, the geometry that we assume for the plume will have a big impact on the entrainment and evolution of the plume and the subsequent melt that plume drives. In thinking about the plumes, I think this is one area where we actually have made a lot of progress. There's still a lot of work to do, but in the past decade, we've had some really exciting developments in measuring the properties and structure of subglacial discharge plumes. This has involved studies like Ken Mankoff's here, where he's got in situ measurements of the plume properties right at the glacier. This example over here from Alistair Everett, using some neat remote sensing observations, looking at the signature of the plume at the surface and actually being able to measure the bulge or the surface elevation from the momentum when the plume hits the surface and back out other properties of the plume subsurface. This is an example of some ongoing work by Bridget Oval, a student working with me, who's using acoustics from ADCPs to map out the spatial extent of these discharge plumes as they rise along the ice face, along with multi-beam sonar shown in the background here. And a lot of this progress has been enabled by new autonomous platforms to get measurements right near the ice where we can't go with boats. These are just 2 examples. The JCIOI developed at Hui, and the autonomous kayak Ross, which now is actually an autonomous rib, developed at Oregon State by Jonathan Nash and his team. And these have really enabled new measurements of not only the discharge plume, but other dynamics near the glaciers that have been inaccessible by sort of standard oceanographic methods. Okay, so from these sort of what I'll call intermediate scale observations of the plumes, I think we are making some progress on constraining some of these parameters. We have some evidence that maybe discharge plumes are a bit more distributed than what we typically used to model them as point sources, that maybe they have a width on the order of hundreds of meters, although we only really have estimates of this width for 1 or 2, maybe 3 glaciers. And so we still have some sort of important remaining unconstrained parameters for how we model sort of the plume side of things. Okay, moving a little bit towards the right and thinking about how these are coupled, this framework assumes that the upwelling velocities of plumes are the only velocities that are driving shear instabilities across the boundary layer. And this is obviously a big problem if you have other modes of circulation that are enhancing the velocity near the ice and then thus enhancing the turbulent transfer across the boundary layer. And this is also an area where I think we're making a lot of progress. But the answer to this question is really going to depend on kind of what regime of melting we're looking at. So if we ask the question, are upwelling plumes the dominant component of velocity adjacent to the ice? That's probably a pretty good assumption, right behind subglacial discharge plumes, where we have a large source of localized buoyancy and high velocities, on the order of a meter per second, rising up the ice face. But this is probably not a good assumption away from the discharge plume in what we could call the ambient melt regime, or it has a variety of names. But over here, where the buoyancy is only from submarine melt itself, the buoyancy-driven plumes should be much weaker, and we expect upwelling velocities on the order of centimeters per second. And so neglecting other forms of velocity in this ambient melt regime is really questionable. And we have growing observational evidence of some of the other sources of velocity that we need to consider. So for example, this is in white in this plot here are some observations of a strong recirculation that's set up by an outflowing discharge plume here. So schematically, that's thinking about some of the recirculations and eddies that can enhance velocity and then thus enhance melt across the terminus. This is just another example showing a similar process, this time from surface velocities derived from tracking icebergs, again showing an outflowing plume and a strong persistent recirculation or eddy along the ice face. Another process is internal waves. This is some work led by Jesse Cusack looking at near-glacier moorings deployed about 50 and 400 meters from the ice. And what he sees is a really strong signal of internal waves that have been excited by the discharge plume and are propagating throughout the near-glacier region. And so this is another source of kinetic energy or velocities across the ice face that are not accounted for in sort of the standard plume melt theory where plumes are suggested to be the only source of velocity. And of course, there are a variety of other modes of circulation and sources of velocity that can contribute here. Oh, and just as a little fun aside, thinking about how we get some of these observations, this is a video showing the deployment of the moorings that I just showed that Jesse Cusack is working with, where you can see a little autonomous kayak here towing a barge, and on the barge is a mooring that's about to fall out through a trapdoor and deploy this mooring right near the ice. Okay, so if we go back to this slide that you're probably getting sick of seeing. So this is definitely, I think we have growing evidence and we're making a lot of progress here that we really need to start thinking about other components of the velocity field to understand, what's driving fluxes across the inner boundary layer. And then as we get, more solidly into the melt parameterization side of things, there are two final things I want to point out. So first, we have these coefficients, a turbulent transfer coefficient and a drag coefficient that are entirely untested at tidewater glaciers. They've been derived from studies of sea ice and ice shelves, which are horizontal ocean ice boundaries, and there's good reason to think they might be quite different at vertical ice faces where the input of buoyancy is destabilizing as opposed to stabilizing. And we also have kind of a classical value of drag coefficients that are usually used that assumes a relatively smooth ice face. Or you could question, is this functional form even the right one for modeling submarine melt? This, again, assumes a shear-driven boundary layer. But if the plume is not energetic enough, we might expect to be in a different regime where we have buoyancy-controlled turbulent convection. And so this plot over here is from a nice review on melt by Elena Malyarenko, showing this transition from a shear control, well, from a buoyancy-controlled regime at less energetic plume velocities up to a shear-controlled turbulent convection regime. And this form assumes a shear-controlled regime, and it's our sort of assumption that this is the right regime for real tidewater glaciers. But most of our glacier-inspired lab experiments, fall in this buoyancy-controlled regime. And I would argue, given what we've learned about how energetic the ocean is right near the ice, that it's likely we're in this shear-controlled regime. And a paper by Craig McConaughey shows that this transition should occur around 3 or 4 centimeters per second, which would, I would argue, suggest we're in this regime. But there's definitely a reason to question the functional form of this parameterization, not just the coefficients within it. And when we get to these questions over here about the melt parameterization, this is where we're really flying blind with observations. Is that 2 minutes, Donald?
Yeah, you've had 20, so if you wrap
okay.
relatively soon, sorry.
Okay.
Yeah, you have a few minutes.
Thanks. So one thing I'll mention is just that, this is an observational challenge because the subglacial discharge plume is often the biggest signal at these glaciers. And so a lot of our recent progress has been measuring the subglacial discharge plume. And discharge plumes should have a strong impact on melt, but melt actually has a very small impact on the discharge plume. So these sorts of observations of transects of plume velocity are helpful for getting into the larger scale plume dynamics, but are really difficult for testing our understanding of melt and boundary layer processes. So we really, I think some of the progress in trying to get at these smaller scale processes needs to occur away from the discharge plume, where melt processes are more apparent. And this is just one example of some surveying right near LeConte Glacier, showing measurements of intrusions from plumes of ambient melt, so away from the discharge plume, where we're actually able to back out some properties related to the melt dynamics. And some of the upshots here are that the ambient melt rates are high, and that, as I mentioned, the non-plume velocities seem really important. And we can sort of explore potential adjustments to coefficients, but we have this problem that it's a really underdetermined problem. There are way too many unknowns, and these sorts of observations alone, at sort of the tens of meter scale, can't constrain some of these important questions in the melt parameterization. So I will just end by mentioning that we just don't have any existing measurements of the boundary layer at any tidewater glaciers. We want to be able to kind of probe the structure of the velocity and temperature field as you go away from the ice, but we're not yet there in terms of getting these observations. We have one ongoing effort with a group of collaborators here at LeConte trying to get some of these boundary layer measurements. So stay tuned. But I'll just end, sorry, this is a little long, and by summarizing that, we have this widely used melt parameterization and plume theory that has given us all sorts of insight into melt, but really hinges on a bunch of untested parts. And our observations so far are suggesting that melt is really underpredicted by theory. And I think, one component of that is some of the new progress we're seeing in measuring all the other components of velocity that can drive melt and enhance melt. So thinking beyond just plumes. But a real challenge for our community is the lack of measurements of the boundary layer. And so the melt parameterization part is really entirely tested, and we need new observations and observing platforms. So I'll end there. Maybe just leave those questions up. And sorry, I went a little over there.
All right. Many thanks, Rebecca. This was a very, very nice insight into the state of the understanding on tidewater glacier ocean interactions right now. We are a bit short on time, so I would just suggest we take a round of common question afterwards, but feel free, everybody, to put your questions already in the chat if you have any to concern to Rebecca's talk. Otherwise, I would give the floor further to Nico Jourdain, who is using mainly models to reduce the uncertainty on sea level projections, and with the focus on ice-ocean interactions in Antarctica.
Yes, let me share my screen. Can you see it?
Yes.
Okay, perfect. Let me put that down. I'm ready to go. Okay, so first, thanks for inviting me to talk about ice shelf in ocean models. It's quite a broad topic, so I'm just going to speak about a few aspects of this. And I have also to specify what I have in mind with ocean models. So I'm only going to speak about these ocean models that you can use for typically climate projections. So ocean models that are run for decades to centuries, that are all based on the three equations that were introduced this morning by Maddie. So these are the questions that I'm going to try to address. Are ice shelf cavities well represented in current ocean models? And to be more specific, are they sufficiently well represented to be included by default in global ocean and climate models? And are they sufficiently well represented to provide melt rates to ice sheet models? Another question that I try to address is what are the wider consequences of ice shelf cavity if ice shelf cavities are not or poorly represented in ocean models? I'm going to start with an example, the example of Ronne Filchner. So the two bottom plots show observational estimates of melt rate. Yellow to red colors are actual melt, and purple colors show refreezing. So these are two estimates based on remote sensing and surface mass balance models from Ronne and colleagues on the left and from Holt on the right. The top panels show the result from two different ocean simulations. One is Nemo at 1/12 of a degree, approximately 2 kilometers in this area. This is from a paper by Ute Hausmann. And on the right, you have the results from Nemo at 1 degree, approximately 25 kilometers here. This is the typical resolution of semi-PSIX models in this area. And this plot is from a paper in preparation by Catherine Hutchinson. So first, look at the 1/12 of a degree and compare two observations. You see that overall, the main pattern is correctly represented. You have large areas of refreezing to the north of the Henry Ice Rise, to the east of Berkner Island, and on the northwest flank of Ronne Ice Shelf. This is quite similar to observations. You have also stronger melt rate next to the grounding lines and along the front as in the observations. If you look at the 1 degree model, you can see that overall you have similar patterns of refreezing and again stronger melt rate next to the grounding line. So a question that we should ask is, are we happy about this melt pattern in climate models? And I guess that the answer depends on what you expect from these models. So here I've shown the temperature and salinity diagram. It's also from the paper by Catherine Hutchinson. On the left, you have the TS diagram with no ice shelf cavity, and on the right, you have the TS diagram with ice shelf cavities. So overall, it's again very similar. But if you look at the pink rectangle, you can see that you have the ice shelf water. It's a water mass that is present in the case of when you have the presence of an ice shelf cavity. So if your research focus is on the water masses, it means that you would probably be sufficiently happy with this kind of ice shelf in your simulations. But now we can look at other parts of the melt pattern. You can have a look at the grounding line that is in the area that is shown by the green circle. And you can see that large areas are missing in the case of 1 degree model. And actually, we don't resolve the narrow channels that we see here. And it's actually a problem for the ice sheet dynamics. And this is what I'm showing here through this plot by Ronne Rees in 2018. This plot shows the buttressing flux response number, and it's actually showing the increase in ice flux across the grounding line when we remove 1 meter of ice. So this shows that in the narrow channels that we don't represent at 1 degree, when we remove 1 meter of ice here, we have a strong response of the ice shelf. So it means that the ice sheet dynamics is very sensitive to melt rates in these narrow channels, but not at all over the rest of the ice shelf. So it means that if the aim is to couple an ocean model to an ice sheet model, 1 degree is probably problematic. And so even the 1/12 of a degree, if we zoom in a little bit more to the melt pattern, and we can have a look, for example, at this pink circle on the left, you can see that in Nemo at 1/12 of a degree, we tend to reproduce quite high melt rates in the channel, but not right at the grounding line as in the observational product. So I have to say that there is probably some uncertainty on the melt product, on the observational product at the grounding line, in part because of the flexural rigidity. But we believe that this is mostly a problem of the ocean models because the water column thickness is too thin next to the grounding line to properly represent the ocean circulation in this part of the domain. So speaking about biases in melt patterns, I have to say that this is also very specific to models. And here I show a few results from ISOMID Plus, so an intercomparison of ocean models with ice shelf cavities. This is from work in preparation by Xyla Assay Davis and with participation of many institutes. And here you have 12 models. So the gray part on the left is the grounded ice, and the gray part on the right is the open ocean, and the color is the melt rate. What you can see is that it's very different from one model to another. First, some models have more noise than others. Some models tend to put most of the melt rates next to the grounding line, whereas for some other models, it's more spread over a larger area. You have also east-west asymmetry that is reversed in some models compared to others. So just to say that there are large also differences across the models. It can be related to many things in the model, but it seems that the vertical coordinate system is one of the very important things. So, okay, it's nice to be able or not to represent the melt rate, the pattern, but if we think about climate projections, it's also very important to know if the models are able to simulate the evolution of the melt rates. Here I'm showing a plot from a paper by Anthony Sayahan and colleagues, and this is based on what I think is the first Earth system model coupled to both the Greenland and Antarctic ice sheets. So this plot in particular shows the evolution of the ice shelf basal melt flux of Pine Island. So the blue line here with the interval shows the observational estimates, and the red curve is the multi-ensemble mean of the SSP 585 scenario, and the black one is the same for the SSP 119 scenario. So what you can see on this plot is that the average melt rate at the beginning of the simulation is close to observational values, so it's quite good, but there is not much evolution of these melt rates with time, and the two scenarios remain very close. And we think that this is not what should happen. And if we look at these results from simulations at 1/12 of a degree from a paper that has just been accepted, you can see that it's quite different. This plot shows the melt rate for 8 ice shelves in the Amundsen Sea. And the blue bars show the present-time melt rates, while the yellow to brownish colors show the future melt rates. And there are 3 bars for each because there is an ensemble of 3 simulations with different set of parameters. If you just look at Pine Island here, what you can see that on average from the present to the future, I have to say that the future here is RCP 85. In this case, you have an increase by 30 to 50% of the melt rate. And actually, the authors of this paper also suggest that this is not a very realistic evolution of melt rate, and they suggest that it's because we have very few grid points for Pine Island at this resolution. Actually, we have 11 grid points at 1 degree, and there are actually several problems related to that. One of them is that there is no ice that is really exposed to the deepest part of the circumpolar deep water. And the second problem is that, as you can see here with the bathymetry, with the topography of the ice draft, you have very flat areas of ice, and this tends to create stable layers of fresh and cold water beneath the ice, which prevents the melt rates to evolve when the condition away from the ice shelf evolve. Okay, so it's maybe not a surprise. 1 degree is not enough to simulate the small ice shelf, but let's look at the large ice shelves. And so in the same couple simulations, you have this evolution of melt rates at Ross and Ronne Filchner. You have something that is pretty flat for several decades, and then suddenly there is a very strong response. Melt rates are multiplied by more than a factor of 10, and become very high in a few decades. And you have the same a bit later for Ronne Filchner in these simulations. So this is pretty similar to the ocean tipping point that was fully described by Hartmut Helmer in 2017. This is the evolution of the melt flux for Ronne Filchner. It's from an ocean model forced by CMIP3 model, HAT-CM3, under the A1B scenario. And again, similarly to the previous plot, you have something that remains pretty flat. And at some point in around 2070, you have a strong increase in melt rate, and then it stays stable for some decades. Interestingly here, if you revert the perturbation back to the 20th century, you get something that remains quite high, and even if the bifurcation is earlier in the simulation, you still get this steady state for high melt rate. And actually, you really need to force the melt rate to decrease for a few years to be able to get back to the present day melt rate with the present day condition. This is quite connected to this paper by Julia Hazel and Andrew Stewart from 2020. They describe the bistability of the melt rate in Filchner-Ronne cavity. So this plot shows the integrated melt rate for different wind perturbation, and each circle is one simulation, one stable simulation. The blue circles are for simulations that start in configuration where the ice shelf cavity is flooded by high salinity shelf water, and the red circles it's for the conditions where the ice shelf cavity is flooded by modified warm deep water. So when you have it means that you can have two stable states under the same wind regime, but depending on the initial condition, it will remain warm or it will remain cold. And if you have a wind perturbation, it will also remain the same way until it reaches a warm state if the wind perturbation is strong enough. And in the case where you reach a warm state, if you revert the forcing, you can actually go back to a state that is different even for the same atmospheric forcing. So, and this balance between the two possible states is really related to the relative density of these two water masses, high salinity shelf water and modified warm deep water. So any process that will affect the relative density of these waters is susceptible to trigger important changes. So in the case of Hartmut Helmer's paper, it was more something like view that a threat that could happen in the future under certain forcing, but you can also have spurious tipping points in ocean models, because as I've shown before, any modification of model parameters that would affect the bottom density of high salinity shelf water or modified warm deep water could lead to a tipping point. So you have here examples from two papers. On the right, you have a plot that was done by Pierre Mathieu using NEMO at 1/4 degree. And these are two different simulations. So this is a meltwater flux, the melt flux from Ross ice shelf. And each curve is for a different set of model parameters. And the only difference between the two is a few values of the sea ice parameters. More specifically, there are different drag coefficient between ocean and sea ice and different snow conductivity over sea ice. The two sets of parameters are commonly used in the NEMO community, but one of them will give a tipping point at some point under present day condition in the Rossy, while the other one will remain stable. The example on the right, it's from a paper by Como and colleagues in 2022 with the E3SM model. They didn't have any issue with the Ross Sea. So the plot shows 200 years of pre-industrial control, the melt flux for Ross on the top, and the bottom one shows Filchner-Ronne. And with the initial set of parameters that they used, they had this big tipping point for Ronne Filchner after 140 years. And they figured out that when they changed the Joint coefficient, they managed to keep it stable. So the Joint parameterization is used to represent the transport of heat and salts by eddies that are not represented at coarse resolution. And so these kind of parameters can affect also the density of waters next to Antarctica, in the same way that sea ice parameters can also affect the density of water masses around Antarctica and then trigger tipping point or not. Okay, so we've seen that there can be biases in the patterns and in the evolution of melt rates in Antarctica, and now I'm going to show a few possible consequences of this. So what is the role of glacial melt in the broader ocean, and what consequences if no ice shelf cavities or if ice shelf cavities are poorly represented? The first example that I'm going to show is the barotropic stream function that we have with ice shelf cavities on the left and without ice shelf cavities on the right. This is from the paper by Pierre Mathieu in 2017. And so basically, the more contours you have, for those who are more familiar, the stronger the circulation. So what you can see is that, so this is West Antarctica, this is the Amundsen Sea, and this is the Bellingshausen Sea. In the Amundsen Sea, if you have ice shelf cavities, you have a much stronger circulation that is going like this all around the Amundsen Sea. And this can be understood in a simple way, that if you put more ice shelf water along the coast, you will increase the horizontal density gradient, and therefore you will change the pressure gradients, and therefore you will change the geostrophic circulation in the ocean. There are also important consequences of ice shelf meltwater on sea ice. This is a plot by a paper by Nacho Marino et al. In 2018, and this is the sea ice thickness trend from the 90s to the 2000s. On the left, you have the trend in sea ice thickness that is due to a change in atmospheric forcing between these two periods. And on the right, you have the part of the trend that is due to more fresh water released by ice shelves over this period. So you see that for most of the areas, when you have more ice shelf meltwater, you tend to have thicker sea ice. But you have a specific behavior in the Amundsen Sea that is also described in other papers, where you have actually, when you have more ice shelf melting, you have more circumpolar deep water that is entrained towards the surface, and that tends to thin the sea ice in this region. You have also a warming of the subsurface that has been described in many papers. Here I'm showing plots from Ben Bronsella, but you have also these studies that are cited here that describe very similar effects. So the first plot shows the average warming along the Antarctic coast that is due to glacial freshwater perturbation up to 1 degree here at 500 meters. I have to say that this is the freshwater flux from the Contour Pollard 2016, so this is probably quite in the high range of what we can expect. But yeah, this paper shows quite a strong response in the subsurface, which would tend to reinforce melt rate in the future. And there are different ways to explain this, but the way it is explained in this paper is that the freshwater at the surface will tend to flatten the isopycnal, and because a lot of the mixing in the ocean is isopycnal along the isopycnals, it means that this will facilitate the mixing of CDW, of circumpolar deep water, towards Antarctica. In this paper, they show that this kind of effects can have climate consequences, and in this case, for example, there is a delay of the air temperature warming of the southern hemisphere by more than 1 decade. We have similar things also when looking more regionally. This is results from a paper by Marion Donamagnan in 2017. And so the two figures show the warming of the Amundsen Sea between 200 meters and 1,000 meters depth in response to poleward shifting winds. And on the left, it's when we force ice shelf melt to remain zero. And on the right, it's when we allow interactive melt beneath the ice shelves. And you can see that the entire Amundsen Sea is much warmer when we have the ice shelf melting, and therefore when we have the ice shelf melt induced circulation in the Amundsen Sea. So I think that I'm towards,
just a few minutes. Yeah, thanks.
So so the take-home messages are that even at 1 degree resolution, representing large ice shelf cavities can have some benefits in terms of water mass transformation. Of course, when we look closer in the details, more work is needed to parameterize melt rate where it matters for ice sheet models. This is in particular in the grounding zone. And this is likely true even at relatively high resolution. It's of course true at 1 degree, but we've seen that even at 1/12 of a degree, we still need probably something to parameterize the melt rate next to the grounding line. Looking at the different groups who have tried to make long simulations with ice shelves, it remains difficult to have high confidence on the model's ability to represent the future evolution of ice shelf melt rates. And sometimes you can see that likely because coarse resolution, you have no response. You can have also spurious tipping points, so that when you have a tipping point in a projection, you can always question whether it's really forced by greenhouse gases emissions or whether it's actually due to choices in the model parameters. And last comments, melt rate biases in ocean models that resolve ice shelf cavities can have wide consequences. But we need to keep in mind that not representing ocean ice shelf interactions is also a problem and a source of biases in ocean models. And I thank you very much for your attention.
Yes, thank you very much, Nico. I'd like to applaud for both speakers at the same time. I think this was two very, very nice, very, very different, but very, very nice talks that really nicely frame sort of the next step problem after we have solved the parameterizations or the turbulence heat flux at the ice-ocean interface, actually how to connect it to the surrounding circulation and eventually get some broader impacts out of that. So I think that was really nice. I don't see any posts in the chat, but I will quickly ask people to raise their hands if there are any questions to either of the talk. Although I don't want to drag it too long, because I also want to give people a little break before we dive into the breakout sessions. But yeah, we to either talks. Are there any comments, questions? There might be a hand here. Donald, do you see?
Yeah, I think it's Fiamma.
Yeah, well, go ahead.
Hey, Tori, Donald, thanks for organizing. This is great. Thanks, Becca and Nico, great talks. I just have a question that I'd like to address to both of you, and one that I think is maybe more of a matter of discussion, but I'd like to hear your thoughts. So we've seen examples from Becca's talk on, modifying really near ice parameterizations, and Nico, you showed some of the challenges in connecting larger scale circulation with cavity circulation and eventually leading to melt rates. So I guess my question is, it's very tempting to work in separating near ice parameterizations from far field parameterizations of transport under cavities or in fjords. But there's, of course, a coupling and a feedback of the near ice processes on the circulation, whether it be a cavity, and how much can we decouple them, or how much are we really, do we need to think about them as a coupled system, which then means that some of the more idealized parameterizations might be really hard to apply, especially in the near ice boundary. It's a nice, easy question for both of you.
Who wants to go first?
I can chime in a little bit. Yeah, I mean, there's a lot of really good questions there. Yeah, I would agree that like these larger scale processes are super important, especially as you think. Well, I mean, I guess in both directions, you think about how the effects of the ocean on the glacier, or the effects of all the glacial meltwater in the ocean. I sort of think of it as like, maybe a first step is getting things right at the smaller scale. How can you relate the near ice properties and buoyancy forces and whatnot to the melt rates? But then, ultimately what you need for larger scale efforts is some sort of more bulk parameterization that accounts for a whole variety of processes at larger scales too. So I would definitely say both. I mean, that's not really an insightful answer, maybe, but I mean, I think there's also an interesting, in tidewater glaciers in particular, when you have a lot of subglacial discharge, if you're looking in the direction of glacier forcing ocean, maybe the submarine melt terminus is maybe like you're that lower down the list after subglacial discharge and maybe iceberg melt. And so I guess what you're working towards really would depend on which direction you're interested in terms of the melt parameterization for a glacier or the boundary condition for an ocean model. That's obviously not a full answer. Nico, I'll let you take.
Yeah, no, I'm not going to give a full answer either. I think that's when you want to parameterize something, to look at observations or things, you need to have a simple problem. So you need to look at something that is quite small, restrained, and a simple case. But then, of course, there are feedbacks. So I think that after you have looked at the simple case, you need to put the rest of the system little by little and show what goes wrong when you couple to everything. But it can go very far, because it can go to the full ocean, then it can go to the coupling with the atmosphere, it can go to many things. So yeah, I don't have a good answer to give. I'm sorry.